Hi everyone, I am Sam. Today we are going to talk about nuclear physics. Our story begins not in a laboratory, but in the mind. Long before we had microscopes or particle accelerators, curious thinkers asked a simple yet profound question. What is the world made of at its smallest level? The ancient Greek philosophers, people like Democritus, conceived of tiny, indivisible building blocks called atoms. They had no scientific experiments to back their claims, but their intuition nudged them toward the idea that if you keep cutting matter into smaller and smaller pieces, you would eventually reach something fundamental and unbreakable. For centuries, this idea lingered as a philosophical concept, rather than a proven scientific fact. The modern journey of nuclear physics, however, would only truly begin once we had the tools to probe nature at scales smaller than we'd ever imagined. Fast forward to the 19th century. Through careful experiments, scientists like John Dalton gathered evidence that matter really is composed of atoms. In these early models, atoms were thought to be the smallest possible units of matter. They were imagined as tiny solid spheres that made up all the substances we see around us. But as we entered the 20th century, the story took a dramatic turn. J.J. Thomson discovered the electron, a tiny negatively charged particle that was smaller than any atom, proving that atoms were not solid balls, but had some sort of internal structure. This was a key realization. If there were tiny electrons inside atoms, what else might we find hidden inside that structure? The answer came from Ernest Rutherford's famous gold foil experiment, a landmark in scientific history. Rutherford and his colleagues fired tiny particles at a thin sheet of gold, expecting them to pass through with minimal scattering. Instead, a few of these particles bounced back, as if they had struck something incredibly dense. This unexpected result led Rutherford to propose a new model of the atom. Most of its mass and positive charge lay concentrated in a tiny, dense core at the center, which we now call the nucleus. Suddenly, the atom had a heart, and that heart was the nucleus, a region so small that if the entire atom were enlarged to the size of a sports stadium, the nucleus would be just a grain of rice at the center. But what is inside this nucleus? Researchers soon found that it contained protons, positively charged particles, and later James Chadwick discovered the neutron, a similarly massive but electrically neutral particle. This understanding didn't just happen overnight. It was the product of persistent questioning, a willingness to challenge assumptions, and a flair for the unexpected. The nucleus, it turns out, is a delicate dance of forces. The protons inside the nucleus repel each other electrically because they share the same positive charge. Yet something holds them together in this unbelievably tiny space. That something is the strong nuclear force, a fundamental interaction that binds protons and neutrons together, overcoming their mutual electrostatic repulsion. It is one of the strongest forces known in nature, and yet it only acts over extremely short distances, roughly the size of the nucleus itself. Imagine trying to keep several fiercely independent people packed in a tiny room. Without a force to keep them cooperative, they'd scatter. The strong nuclear force is like a powerful but very short-range glue that keeps everything bound tightly in the nucleus. Understanding the nucleus and its behavior opened the door to many questions. How stable are different atoms? Why do some last forever while others spontaneously change, emitting radiation in the process? What happens when you alter the nucleus itself? In the early 20th century, scientists began to realize that certain atomic nuclei could transform spontaneously. This process, known as radioactivity, had first been discovered by Henri Becquerel and later investigated by Marie and Pierre Curie. Radioactivity revealed that atoms were not as unchanging as once believed. They could break apart or rearrange, changing from one element into another. This was a startling concept, practically alchemical in nature, but it was grounded in observable phenomena. At this point, the groundwork was laid for perhaps the most dramatic realization of all, that vast amounts of energy are locked inside the nucleus, waiting to be unleashed under the right conditions. The key breakthrough came with the discovery of nuclear fission, splitting heavy nuclei into smaller ones, by Otto Hahn and Fritz Strassmann, and the explanation by Lise Meitner and Otto Frisch. When a heavy nucleus, such as uranium-235, absorbs a stray neutron, it can become so unstable that it splits into two smaller nuclei. In the process, some of the mass converts directly into energy, as described by Albert Einstein's famous equation E=mc². Even a tiny amount of mass can yield a tremendous amount of energy. This insight would permanently change the world. Once scientists learned how to trigger fission in a controlled manner, they realized they could set off a chain reaction. One nucleus splits, releasing more neutrons, which then split more nuclei, and so on. This chain reaction could be slowed down and harnessed to produce steady energy in a nuclear reactor. Alternatively, if allowed to proceed at full speed without moderation, it could release a devastating explosion in the form of an atomic bomb. It's a sobering fact that the pursuit of understanding the nucleus eventually led to one of humanity's most fearsome weapons. The Second World War and the development of the atomic bomb would etch nuclear physics into the global consciousness, overshadowing, at least in the public eye, the quieter progress in understanding the atom's secrets for more peaceful ends. But nuclear physics is not just about bombs and power plants. It's about understanding the fundamental nature of matter. One crucial piece of the puzzle is how nuclei behave under different circumstances. Some nuclei are stable, happy to remain as they are for billions of years. Others are unstable, prone to decay into different elements. During these decay processes, alpha decay, beta decay, gamma emission, energy and particles are released. While these radiation processes can be dangerous if not handled properly, they are also key to many modern technologies. Smoke detectors, for example, often rely on a tiny amount of radioactive material. In medicine, radiation therapies help battle cancer, and certain radioactive isotopes serve as tracers in medical imaging, providing insights into the body's inner workings. Nuclear physics also teaches us about the origins of the elements in the universe. The Big Bang produced mostly hydrogen and helium. The heavier elements, the carbon in our cells, the oxygen we breathe, the iron in our blood, were forged much later, deep within the fiery furnaces of stars. As stars run through their life cycle, they fuse lighter nuclei into heavier ones. This process, known as nuclear fusion, releases a tremendous amount of energy and is what makes stars shine. Eventually, when massive stars die in violent supernova explosions, they scatter these heavier elements across space. Over time, this cosmic debris reassembles into new star systems, new planets, and ultimately into us. In a sense, understanding nuclear physics allows us to trace our own existence back to ancient stellar furnaces. Every atom of calcium in your bones and iron in your blood was once inside a star that lived and died long before our Earth formed. Fusion, the joining of light nuclei to form heavier ones, is the opposite of fission. While fission splits heavy nuclei and releases energy, fusion merges light nuclei such as hydrogen isotopes to produce helium and other heavier elements, also releasing huge amounts of energy in the process. Fusion is what powers our sun, providing the heat and light that makes life possible on Earth. For decades, scientists have dreamed of harnessing controlled fusion on our planet. If we could achieve it sustainably, fusion power could provide a clean, virtually limitless source of energy. Unlike fission, fusion does not create long-lived radioactive waste. But mastering fusion has proven a daunting challenge. The conditions needed, extreme temperatures and pressures to force nuclei together, are not easy to recreate and sustain. Yet research continues, with massive international projects working toward a future where fusion reactors might light our cities, heating our homes, and powering our factories with the energy of the stars. Stepping back from these grand applications, it's worth remembering that nuclear physics is also a sophisticated, beautiful theoretical framework. At the deepest level, understanding nuclei involves quantum mechanics, the strange and often counterintuitive rules that govern the behavior of matter at the smallest scales. Particles sometimes behave like waves. Their positions and velocities can only be expressed in terms of probabilities. Protons and neutrons themselves are not fundamental. They are made up of even smaller particles called quarks, bound together by particles known as gluons. Delving into this world, we find that the nucleus is more like a tiny seething cluster of energy and fields rather than just a handful of billiard balls stuck together. Nuclear physics also interfaces with other branches of science. Nuclear magnetic resonance, for example, is the basis for MRI scans, revolutionizing the way we look inside the human body without cutting it open. Understanding nuclear reactions helps archaeologists date ancient artifacts through radiocarbon dating. Geologists learn about the Earth's past climate from the isotopes locked in ice cores. The study of nuclear processes gives insights into neutron stars, some of the densest objects in the universe, where matter is packed so tightly that entire atoms collapse and neutrons reign supreme. In the modern world, nuclear power plants generate a significant fraction of electricity for many countries. They do so without emitting greenhouse gases, which makes nuclear energy an attractive option in the context of climate change. However, the industry has faced challenges. Catastrophic accidents like Chernobyl and Fukushima have underscored the importance of strict safety protocols and robust reactor designs. Spent nuclear fuel, which remains radioactive for thousands of years, poses a long-term waste management problem. Scientists and engineers are working on new reactor types, such as small modular reactors, or those that can burn different kinds of fuel, to address these safety and waste concerns. And while these problems are not trivial, the potential benefits of safer, cleaner nuclear energy continue to inspire research and innovation. It's often said that nuclear physics unlocked the secrets of the atom, but it also unlocked new questions, spurring new fields of research. What happens at the edge of nuclear stability? There are exotic nuclei with unusual ratios of protons to neutrons that exist only fleetingly before decaying. Yet studying them helps us understand the forces at play inside all matter. How do these insights shape our theories of the fundamental interactions in nature? Even as we speak, particle accelerators and large research facilities around the world are probing nuclei under extreme conditions, looking to refine our understanding and maybe, just maybe, open a window onto new physics beyond what we currently know. The storyline of nuclear physics is thus one of constant interplay between theoretical insight and experimental discovery. It is a narrative rich with characters, brilliant scientists who wrestled with nature's riddles, engineers who built machines to test daring hypotheses, and entire societies adapting to the implications of these new powers. It is a story that has swung between hope and fear, promise and peril. On one side, we have the potential for almost limitless clean energy and incredible medical benefits. On the other, we have the somber legacy of nuclear weapons and the daunting problem of radioactive waste. Understanding this dual nature is part of coming to terms with the science itself. Like discovering fire, cracking the nucleus changed humanity's relationship with nature. Whether that's for better or worse ultimately depends on how we handle this powerful knowledge. For someone without an academic background, the world of nuclear physics might seem cloaked in mystery. Yet as we unfold the story, it becomes clear that it's not just a bunch of strange symbols and equations. Rather, it's a narrative about how we learned that the building blocks of matter hold within them unimaginable forces. About how an atom's heart can change shape and form, releasing radiation or energy that we can harness or that can harm us. About how we came to realize that everything around us, including ourselves, is shaped by nuclear processes that happened billions of years ago in distant stars. We began with ancient philosophers pondering the nature of matter. We have traveled through centuries of inquiry, stepping from one discovery to the next. We saw how the atom, once imagined as a solid sphere, turned out to be mostly empty space with a tiny nucleus at its center. We peeked inside that nucleus to find protons and neutrons bound together by the strong force. We watched as radioactivity taught us that atoms are not eternal and unchanging. We learned that splitting heavy nuclei can produce power and terrible weapons, while fusing light nuclei is what fuels the stars. We recognized that nuclear physics touches our everyday lives, from the electricity that powers our homes to the medical treatments that save lives, and the cosmic history that explains our very existence. When we stand at the edge of the nuclear forest now, it no longer seems so frightening or impenetrable. Instead, we can see pathways and clearings. We might not become nuclear physicists overnight, but we can begin to appreciate how this domain of science arose from curiosity and careful observation. We can see how it has shaped history, technology, and our understanding of who we are and where we come from. Nuclear physics is both a cautionary tale and a beacon of possibility. It reminds us that knowledge can grant us tremendous power, and that with power comes responsibility. It encourages us to keep exploring while being mindful of the consequences. As we leave this introduction behind, remember that what we've sketched is just an outline. Entire fields of specialized research exist within nuclear physics, each with its own intricacies and deep questions. Yet even this brief journey shows that nuclear physics is not something remote and irrelevant, locked away in academic journals. It's deeply woven into the fabric of our modern world, influencing our energy sources, medical techniques, environmental strategies, and understanding of the universe. If nothing else, let this story spark an appreciation for the complexity and wonder of the natural world. Just as the smallest seeds can grow into enormous forests, so can the smallest building blocks of matter shape the vast tapestry of life, technology, and knowledge that make us who we are. That's all for today, and I'll see you in the next episode.